All right, one of the first things we've never really talked about was sampling and something called sample rate and bit depth. And the reason I want to talk about it is it's one of those basic things that you need to know because you run into it in a whole lot of different places. For example, anytime you're playing a CD, you're basically doing sample playback. Anytime you're recording audio on your phone with any digital device, you're sampling. Now, I know sampling originally was you take a snippet of audio that you borrowed from another record and you're using it in your record. And yeah, that's a legitimate use, but it's kind of limited. So the two things you're going to run into are sample rate and bit depth. And I've got this linked already in D2L, by the way, and there's an article there you can look at for more details if you'd like. And I'm trying to not be very technical on it, but it's good to have a basic understanding of this because it affects how you record, regardless of how it is you're recording. And so you run across these settings. So the two primary settings you'll see is sample rate and bit depth. Sample rate is talking about how many snapshots are you taking per second and how many numbers are you using to represent those values. So what happens if there is a kind of sound called a sine wave, and if you were to graph it, it looks like this. And it sounds like this. That's the absolute simplest waveform you can have. Anything else that sounds much more interesting has a lot of jaggies in it. But basically, this is what you're seeing here in this drawing. That is one cycle. So when you say A440, we would have 440 of those a second. That note. This is guerrilla miking. I'm just moving the mic over in front of the speaker. All right. So what happens when I'm going to erase that? Let's get several of these, and I'm freehanding it, so you'll just have to imagine that that's a wave, sine wave. So what happens, that is a graphical representation of what's happening with the speaker. So let's say that line represents the speaker is at rest. And then at some points, the speaker is pushing air towards you, and at some points, it's pulling away from you. Remember, that's that whole compression, rarefaction stuff we talked about way back at the beginning of the semester. So this graph is a representation of the speaker moving forward, coming back, moving forward, coming back. And with a sine wave, it's very, very symmetrical like that. The big problem we have with digital is that, you know, our ears are analog, so it does an infinite number of values between 0 and 1. And this is -1. If we assume 1 is speaker moving towards you, -1 is speaker moving away from you. Well, digital devices don't do that. They can't have an infinite number of values like an analog system like our ears or microphones can. They've always got to be, they call it discrete values. In other words, it can either be 1.2 or it can be 1.3. Well, what if it was actually 1.25? Let's assume our system, because we used cheap parts, could only do the tenth. It can't do hundredths. It can only do tenths. Well, if we have a value that's 1.25, then it gets sliced and becomes 1.2. So that is an error. And they have a name for it called quantization error. I'm going to show you that in a second. So everybody, does that kind of make sense? We've got a digital system that can only measure things very, very precisely. It can't have anything in between. And then, but we're trying to measure an analog value. So what happens here, the speaker is moving forward, and that air hits the microphone, and the microphone goes into a digital circuit, and the digital circuit says, at this point in time, the value is 1. And here it's 0.9, and here it's 0.8, et cetera, et cetera, et cetera. All right, so that's kind of what I was just talking about. That's a real sine wave. different scale there. They got 5 and 10 and -5 and 10. So you got the speaker pushing out towards you, speaker pushing in. So if it's a higher pitch, that one, it's moving many more times a second. You know, this is 440 times a second. That would be 880 times a second, 1760 times a second. So it's just the number of times it's pushing back and forth changes depending on the pitch. All right. And I've got a link here if you want to listen to 111 hertz. So that is somewhere around 442, 20, 110. That's somewhere around B flat, an octave and a bit below middle C. So here's the problem. Like I said, computers deal with very precise numbers. So there's no it's about. It's either this or it is that. If the value is in between, then it gets rounded up or down. So what's happening with sampling is you've got a circuit, a digital circuit that's looking at an analog signal coming in and saying the value at this point in time is this. At this point in time, it's this. At this point in time, it's this. At this point in time, it's this. Okay, kind of float with me for a second. This will make a lot more sense here in a second. The problem with the errors in audio is that what you record in will not be what you get when you play it back. Okay? And that's always been a problem. It was a problem with cassette tape. You know, you would record stuff on cassette, and what you get back would not match what you recorded in. So the solution, theoretically, use higher numbers, higher settings to more accurately represent the audio. Let me repeat that. So we can use higher numbers, higher settings. So let's add another page here, or go to another page. So I've got my waveform here, and there's my zero line. Now, if I took a snapshot here and here and there, and we're going to pretend like those are all even in time. So what happens when you do sampling is the computer comes up with a number, and it says, all right, that's -0.1, and this is 1, and that is 0, and that is -1. That's 0 more or less, plus 1, and then we'll assume there's 1 there called 0. All right, so then let's draw our line again. So what it does, remember it was, I forgot what it was, -0.1, then 1. So we had -0.1, 1, 0, -1, 0, 1, 0, -1. So that's on recording. On playback, here's our zero line. It tries to duplicate that. And so what you get is this. Except I got an extra one there. And this waveform does not look very much like that one. So that's the problem. Now, if I took, I'm going to change colors here. So let's take a whole lot more values. So instead of, we're going to double the number of values we take, the number of snapshots. So now you got the -1. We'll call that 0.5, 1, 0.5, 0, -0.5. Just imagine that these numbers are correct. -0.5, etc. So now our numbers, 0.5, 0.5, -0.5, -0.5, 0.5, 0.5, 0, -0.5. So all of a sudden, we get this. Now remember, I'm graphing these, so I've got, use a different color. I don't like that one. I already used red. brown. This got 0.5, 1, 0.5, 0, negative 0.5, boom, 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 boom. I'm out of room there. So now you can start seeing it's rounding off a little bit. So the more slices I take in that same amount of time, the more accurate my playback is going to be. And that's really what sampling is about, is making sure you get enough slices. Now, so this is an example. It talks about quantization. Well, I'm sorry. The bit depth is how many numbers I can use to represent. The sample rate, how many snapshots am I taking in a standard amount of time. So what this chart shows you is that if I use a greater bit depth, a deeper bit depth means I've got more numbers used to represent the numbers. It's kind of the same thing as placeholders. You know, having 1 decimal place is less accurate than having 7 decimal places to represent something. And that's what's happening here. We've got on that left one right here, right there, switched. I've only got 3 possible numbers, 0, 0.5, and 1. And you can see there that dotted line represents the original waveform. The solid line represents what happens on playback. And you can see the playback does not look very much like the original. If I use more bits, instead of 3 possible values, I've got what? 8, 1, 2, 3, 4, 5, 6, 7, 8, 9. From 0, we'll say 0 to 1 and whatever. So you can see this resulting, again, the dotted line is our original waveform. The solid one is what happens when we play it back. And you can see this B would sound more like the original than A does. So that's bit depth. And then so if you increase the sample rate as well, take more slices, more numbers, more snapshots in a given amount of time, you see how much closer. It's still stair-steppy, but it's much rounder than that first one. So the bottom line is, the higher the bit depth, the more accurate the playback. The higher the sample rate, the more accurate the playback. And remember, sample rate is how many snapshots am I taking per second? And bit depth, how many numbers do I have available to represent those numbers? You can think of it as places in a decimal. For our purposes, that works just fine. And I took some screenshots. This is from Studio One. This is where you would see all this stuff. When you're exporting a mix, if you choose AIFF, you can choose 8-bit up to 32-bit. And with sample rate, when it says resolution, that's bit depth. Sample rate, there's all your options. Even if you're doing MP3, you've got sample rate, 3 options there, and bit rate. Bit rate's slightly different, but the same principle applies. Higher number, better quality. And I don't want to get any more technical than that. So that's the big thing to remember, is the higher numbers, better the quality. But it also means bigger file sizes. So there's this balancing act you have to do. Yeah, Iris, keep typing. It popped up. So there's your advice there. Bigger files do take up more room on your device, take longer to upload, but use the best quality you can afford. And by afford, I mean space on your thumb drive. Do you want the file to take an hour to upload or 20 minutes to upload?